Right now, inside data centers you've never heard of, corporations are burning through their entire annual AI budget in under 60 days. Not because the software is expensive, because the machines are eating themselves alive. By the end of this video, you will understand why the most advanced software on Earth is completely, brutally subservient to the oldest laws in physics: thermodynamics.
Here's what nobody tells you about artificial intelligence. Every time you ask a chatbot a question, you are not triggering a spark of digital magic. You are ordering a warehouse full of machines to drag a concrete block across a rough, unfinished factory floor. That's what a single AI token actually is. Not a byte, not a line of code, a physical load dragged across a physical surface, generating physical resistance. And resistance means friction, and friction means heat. Every single word an AI generates for you creates a tiny explosion of thermal energy inside a silicon chip smaller than your fingernail. Multiply that by billions of tokens generated every single hour across thousands of chips stacked in racks the size of shipping containers, and you get something terrifying. A facility that behaves less like a computer and more like a blast furnace that never sleeps. Picture the factory floor again. Now imagine that floor is packed wall to wall with workers, all dragging concrete blocks at the exact same time in the exact same direction without stopping. That's a single AI response. Not one block, thousands of blocks dragged simultaneously every fraction of a second, 24 hours a day. The friction doesn't happen once, it happens constantly, relentlessly, in overlapping waves that never let the floor cool down. To comprehend the scale, consider what happens inside a single processing unit. Modern AI processors are etched with billions of microscopic gates. As electric current slams through these gates billions of times per second to calculate probabilities, the copper and silicon offer raw resistance. This resistance generates intense localized heat flux, concentrated on a surface area no larger than a postage stamp. If you do not pull that heat away instantly, the internal temperature of the chip scales past critical thresholds within milliseconds. The microscopic pathways inside the silicon literally delaminate, fracturing the crystalline structure and rendering a $10,000 component completely useless. This is the part everyone gets wrong. They think the expensive part of AI is the intelligence. It's not. The expensive part is keeping the machine from melting. So corporations built armies of machines to fight the heat. This is where the real money disappears. Picture a system pumping millions of gallons of subcooled water, not through garden hoses, but through high-pressure steel arteries, thick enough to survive industrial force. This water doesn't just flow. It gets violently forced through micro-channel heat exchangers, stripping thermal energy off silicon at a rate that would boil an ordinary pipe system in minutes. These aren't small systems either. We're talking about industrial plumbing on the scale of a chemical refinery, running around the clock, monitored by engineers whose entire job is making sure a single valve failure doesn't cause a chip meltdown worth millions of dollars. One clogged filter, one pressure drop, and racks of hardware start cooking themselves within seconds. To maximize heat extraction, modern infrastructure cannot rely on ambient air or standard air conditioning units. Air is a thermal insulator. It cannot absorb energy fast enough. Instead, engineers must submerge entire racks of computers directly into specialized dielectric fluids, or use direct-to-chip liquid cooling plates. The mechanics are brutal. Chilled water must be driven at extreme velocity, right against the copper backplates of the chips. The boundary layer of fluid must be constantly stripped away to prevent the water from forming microbubbles of steam, which would instantly act as an insulative thermal barrier and fry the processor. Now scale that up. A single AI data center can demand more electricity than a mid-sized city. That power doesn't arrive gently. It slams into transformers and substations built decades ago for a world that never imagined this kind of load.
Engineers have recorded actual physical vibration in power grid infrastructure, cables humming, transformers straining, because the megawatt demand spikes so violently and so fast. This is not a metaphor. Power grids are physically shaking under the weight of artificial intelligence. When thousands of multi-node clusters simultaneously spin up to train a foundational neural network, they draw hundreds of megawatts of power in a microsecond. This sudden, violent draw creates a massive drop in grid frequency. The massive copper windings inside utility transformers experience extreme electromagnetic forces, causing the physical metal housing to thrum and shake. If the grid cannot balance this load instantly, regional safety breakers trip, causing localized blackouts. And here's the brutal financial twist. This infrastructure has to be built before a single dollar of AI revenue comes in. You cannot rent a cooling tower. You cannot lease a substation upgrade overnight. Corporations are sinking hundreds of millions into concrete, copper, and steel, betting that the software built on top of it will eventually pay for the physical war beneath it. So, when a corporation announces a multi-million-dollar AI investment, most people picture engineers typing code. What they should picture is a construction crew pouring reinforced concrete for cooling towers, running industrial plumbing rated for extreme pressure, and negotiating directly with power utilities just to keep the servers from cooking themselves into scrap metal. The software is almost free. The physical war against heat is what bankrupts budgets. Before we go further, if this is the first time you're seeing how much brute physical machinery sits behind every AI answer you've ever received, this is exactly why this channel exists. We track the invisible, high-friction machinery quietly running the modern world, the systems nobody sees until they break. Subscribing means you get plugged into that system the moment we dismantle the next hidden mechanism. So if this is opening your eyes even slightly, hit like, drop a comment with what surprised you most, and subscribe so you don't miss what we tear apart next. Now here's where it gets financially brutal. This is the part that quietly bankrupts companies who thought they were just buying more compute. Most people assume that to double your AI power, you just buy double the chips. Linear thinking. Simple math. But thermodynamics doesn't obey simple math. Heat doesn't scale in a straight line. It scales exponentially. Cram twice as many chips into the same physical footprint and you don't get twice the heat. You get a compounding thermal catastrophe, because every chip is now packed tighter, fighting for the same limited airflow, the same limited water pressure, the same limited electrical headroom. Think of it like packing more and more workers onto that same factory floor. 10 workers dragging blocks generate manageable friction. 100 workers on the same floor generate overlapping waves of friction that start baking the ground itself. 1,000 workers and the floor doesn't just get hot, it starts to warp, crack, and fail structurally. That's what happens inside a data center when chip density rises faster than cooling capacity. To survive that, you can't just add machines, you have to rebuild the entire physical fortress around them. New cooling towers, new water infrastructure, new substations, new reinforced flooring to hold the weight. Each doubling of power doesn't cost double the money, it costs exponentially more, because you're not fighting software limits anymore. You're fighting the raw physical ceiling of how much heat matter can absorb before it fails. The physics behind this ceiling involves fluid dynamics and thermal gradient limits. As water passes over a row of hot chips, it absorbs heat. By the time that water reaches the third or fourth row of processors in a dense rack, its temperature has already risen significantly. Its capability to absorb further heat drops sharply because the thermal differential between the silicon and the liquid has narrowed. To fix this, you cannot simply pump the water faster. Fluid resistance inside the microchannels scales dramatically with velocity. You must completely re-engineer the hydraulic loop, introducing larger, high-consumption pumps and thicker steel manifolds. The infrastructure required to manage the fluids scales much faster than the actual computing capacity you gain. This is exactly why so many companies without deep infrastructure roots are hitting a wall. A company that only knows how to write code has no answer for a cooling tower that needs to move millions of gallons of water per hour. They can out-innovate almost anyone in software, but they cannot out-innovate physics. You cannot write a clever algorithm that convinces water to absorb heat faster than its molecular structure allows. The wall isn't digital, it's structural, it's mechanical, it's physical. This is why you're now seeing AI companies quietly transform into industrial companies, signing decade-long power contracts, buying land next to nuclear plants, building their own substations instead of waiting for utilities. That's not a software strategy. That's the strategy of a corporation that finally understood it's not in the intelligence business, it's in the heat management business. By nesting data facilities adjacent to nuclear power generation stations, these entities bypass public high-voltage transmission lines entirely. They are tapping directly into the massive, high-inertia steam turbine generators of the nuclear plants. This provides a raw, uninterrupted river of electrons capable of absorbing the extreme, violent load steps required when training complex networks. Furthermore, these locations offer access to enormous, pre-permitted water loops originally designed to cool the nuclear reactors themselves, providing the massive thermal sink required to dump gigawatts of computing heat. And that brings us to the real lesson buried underneath all of this. For years, we were told the future belonged to whoever wrote the smartest code. That story is dying in real time. The future of global technology and the survival of the corporations racing to control it is not being decided in a software repository. It is being decided on power grids, in cooling plants, in the sheer physical capacity of heavy industrial infrastructure to absorb, move, and dissipate impossible amounts of heat. The company that wins the AI race in the coming years will not be the one with the cleverest engineers. It will be the one that can physically survive its own machines, the one with the water, the power, and the steel to keep the furnace from consuming itself. Software promised us a weightless, invisible future. What we got instead is one of the most physically demanding infrastructure build-outs in industrial history, hiding in plain sight behind a chat window. This is just one hidden mechanism running underneath the modern world. There are dozens more like it, systems quietly straining under weight most people never think to question. We'll keep pulling them apart, one by one, so make sure you're here for the next one.